Okay, question 2. Okay, so the switch was closed for a long time before t equals to 0. Okay, at time t equals to 0, the switch is open. Okay, determine the value of the capacitance C needed so that the voltage remains greater than equal to 9 volts for 2 seconds after the switch is open. Okay, so let's look at it step by step. So the first information we have is this. The switch was closed for a long time. So if the switch is closed for a long time, okay, that means at basically t equals to 0 minus, we can say that the current has already been flowing in the circuit because the switch is closed. So we can say that the capacitor or the circuit has reached steady state. So the capacitor is open circuit. Okay, so the capacitor is open circuit. Okay, what do you have? You basically have a circuit that just looks like this, correct? 20 volt, 1k, another 1k here. Okay, so with that we can say that this voltage here VC is equal to the voltage across the 1k resistor, okay, which will be equals to 10 volts. Why? Because it's just a simple voltage divider, correct, between the two 1k resistors. All right, so that is the initial voltage, all right, at time t equals to 0 minus, all right, and at t equals to 0 plus, okay, we say that it is also the same as 0 minus, which means that VC is still 10 volt. All right, this based on the principle that the voltage cannot change instantaneously. Okay, the voltage cannot change instantaneously, okay, across a capacitor. All right, and then the last thing is at t equals to infinity. Okay, so at t equals to infinity, what happens? All right, so when this switch is open, here, the 20 volt supply is no longer part of the circuit because it is already open. Okay, so there's nothing coming from 20 volt. So the only thing that is left is this. All right, one capacitor and one resistor. So from the studio, you know that if you remember the similar setup that we had, okay, where you flip the switch, then from charging you discharge the LED, what happens? Your capacitor will discharge through the circuit, correct? The current will flow, okay, through the resistor in this case, and it will discharge, okay, and it will discharge until there is no more charge left, correct? That means the voltage across the capacitor would then become 0, okay, because it becomes fully discharged in the closed loop that you have here. So at t equals to infinity, we can say that VC will be equals to 0 volt. Okay, this is the case where it is fully discharged. Okay, so that is the first step we need to do. We need to look at what is the situation at 0 minus, 0 plus, and infinity. All right, so once we have this understanding, we can go ahead to put it in the expression. Okay, so that expression is the one that we have in our slides. Okay, so VC t is equals to VC 0 of E minus t by tau plus VC infinity of 1 minus e to the minus t by tau. Okay, so tau is basically your RC. Okay, so from this analysis, we know that the VC0 in this case is 10 volt and VC infinity is 0. All right, so with that, we can ignore the second part of the expression here, right, and just focus on the first part. Okay, so what we have is we have an expression, okay, that says that the voltage across the capacitor is 10 e to the minus t by tau. Okay, and what do we want? We want that at time equals to 2 seconds, the voltage, okay, across the capacitor will remain at least 9 volts. Okay, that means when t is greater than or equal to 2, I must make sure that it's greater than or equal to 9 volt. Okay, that means 10 e to the minus t over RC. Okay, in this case, this t here is 2, okay, because must be greater than equals to 9. Okay, sorry, where is the e? Sorry. All right, so this is the expression. Okay, so of course, once you get this, the rest is your maths, correct? You bring the 10 over, you do the natural log and so on. Okay, so that part I will leave it to you to do in a calculator. So eventually when you solve for this, you get RC greater than equal to 19 seconds. Okay, so from here to here is just the mathematical steps, okay, which I believe you should know. So if you're not sure, maybe I'll just show you. Okay, so you take e to the minus 2 over RC. I just show you for one question, so the rest you can do. Okay, 9 over 10, correct, and then you take the natural log of both sides. Okay, and then when you do the natural log of both sides, then you can bring the power down, correct. So you'll get minus 2 over RC greater than equal to negative 0.1. Okay, and then the rest you can solve it. Okay, then eventually you solve it, you come to this. Okay, so since we know the value of R, okay, we know the value of R, which is 1K, so we can substitute that value inside here, and then we will get that C must be greater than equal to 19 over 1000, which must be greater than equal to 19 millifarad. Okay, so when your capacitor is 19 millifarad or larger, then we can guarantee that at 2 seconds after the switch is open, the voltage will still be at greater than or equal to 9 volt. So this condition will be satisfied. Okay, if my capacitor is greater than equal to 19 millifarad. Okay, so that is the first part. Okay, so in part B, determine the energy that was stored in the capacitor at time t equals to 0 minus. So at time t equals to 0 minus, we know that this voltage here is 10 volt. Alright, so the energy would be equals to half CV square, which is half 19 milli, and 10 square, which will be 0.95 joule. Okay, so sketch the capacitor's voltage versus time. Okay, so how will we do this? So we know that you're going to start off at 10, all right, and 1 tau. Okay, so what is 1 tau? Tau is RC in this case will be 19 milli times 1K, which is 19 seconds. Okay, and 5 tau is equals to 5 times 19, which is equals to 95 seconds. All right, so these two are significant values. All right, if you look back at the notes, why are they significant? Because at tau you would have dropped to 36.8% of the original value, and at 5 tau you are almost close to zero, fully discharged. Okay, so we can say that at 95 seconds, okay, is where you would have almost fully discharged. Okay, something like that. Okay, and at the point of 19 seconds, okay, let me redraw this a bit. Okay, so at 19 seconds, okay, you would have hit 3.68 volt. Okay, 36.8% of the original start value. Okay, that's why we always take tau and phi tau as the two key points in drawing the waveform here. Okay, so it's exactly how you saw it in your slides as well, your lecture slides.